Hello, welcome to another of my short videos on computing fundamentals. Today I'm going to talk about Boolean algebra rules. So in order to understand this video, you need to have some prior understanding. It would be useful if you knew some basics of Boolean logic, the three operators and, or, and not. I'm going to use the terminology, the double ampersand for and, the double bar for or, and the exclamation mark for not. It'd be also helpful if you knew something about Venn diagrams. There's going to be extensive use of Venn diagrams in this video. And if you had some understanding of basic normal algebra, that would be useful. Yes, we're in algebra, don't be too scared. So what is the point to Boolean algebra? Well, you may have seen Boolean logic and representations of a number of statements bound together and some outcome. Here's a fairly complicated, relatively complicated formula using 1, 2, 3, 4 different statements bound up with several of our operators. This looks quite complicated. When you start delving into digital electronics and Boolean logic, you will find that you get Boolean logic statements that are quite complicated very quickly. And one thing that's very useful is being able to take large formulae like this and to reduce them, to make them into smaller formulae. If you're involved in digital electronics, then you will find that this enables you to save money by using fewer logic gates. So the question here is, can we reduce any parts of this formula? One of our rules that we're going to be looking at is what's called one of the absorption rules, and I've got that underneath here. I will talk more about that a little bit later in the video. I just want to show the usage of one of the rules here. It just so happens that I've done it in exactly the right format, and you can see that term is up there on the left hand side. And so because this term A and brackets A or B close brackets is equivalent to A on its own, we can substitute A in there. And these rules that we're going to look at for Boolean algebra are all about the ability to manipulate formulae and to be able to reduce them down to smaller terms. So before we kick into that, there's a couple of ideas that I want to bring forwards, which I'm going to be using in the video. So the first one is, we've just seen this and I kind of glossed over it. We're using a triple bar equals, which means equivalent to, which is a mathematical symbol. It's basically a special version of an equal sign. The next concept is that of universal truth. It can be arguable whether in real life there is such a thing, but within our frames of Boolean logic and logic statements, we can have such a thing. So I'm just going to think of an example, a logical statement that's always true. I could think of some disparaging comment about a politician, but I'm going to actually fix with gravity pulls downwards. And I'm going to claim that that is always true. This can be represented by the word true. And here's the Venn diagram for true. There is the whole screen filled in. Every possible circumstance that we could have has this value as being true. So the corollary of this is a statement which is never true. And here I have the statement, I am interested in football. Never true. I have no interest whatsoever in football. So we're going to represent this with the keyword false. And the Venn diagram for this is very simple. It's empty. There's nothing there. There are no points or pixels on the screen that have been turned into our dark grey, which means a positive result. So let's get on with it. Let's start looking at some of these rules. We've got quite a few to do. And what I'm going to do is I'm going to go through them all one by one, but I'm going to go fairly quickly. So if you're unsure of what's been going on, feel free, obviously, to pause the video, go back, go over things again and again as you need to. And what I'm going to do is I'm going to use Venn diagrams to prove these rules. It would be useful for you to become quite familiar with these rules if you're going to be doing Boolean algebra. So the first set of rules we've got are commutative rules. These are really, really simple and straightforward. Basically, it says you can swap things around. Let's look at each in turn. A and B is the same as B and A. Well, it seems self-evident. Let's prove it. Here's the Venn diagram for A and B. Here's the Venn diagram for B and A. Yes, they're the same. Right, the other one, A or B is equivalent to B or A. Here's the Venn diagram for A or B, and here's B or A. Yes, they're the same. We've proved them. Slightly more complicated now, associative rules. So let's do each one at a time. But the high-level idea is that when you have the same operator, the order of evaluation is not important. So, first one of these, A and B in brackets and C is equivalent to A and brackets B and C. Okay, here we go. So we take the first term, A and B. Here's the Venn diagram for A and B. It's the intersex between the two. Here's C. Here's the two of them combined, A and B and C. Now what I'm going to do all the time as we're going through these proofs is that when I combine two terms, I will show where they overlap in a dark grey and where they don't overlap, but we have had truth from the two different statements or the two different variables involved will be in a lighter grey, a slightly bluey grey. Yeah. And when we're combining them using an and, that bluey grey will fade to disappear. When we're combining them using an or operation, that bluey grey will become the darker grey. If we're using an and, we only want where they coincide, where both things are true. If we're doing an or, we want it to show where either of them is true. Okay, so here we go for this. We've got A and B and C. And because it's an and, the light blue fades away and we're left with just this nuggety shape in the middle there. Let's use the other term, the other side of this rule. So we've got A and the other one is B and C. Combine the two together, we've got A and B and C. And because it's and, again, we fade away the light blue and we've still got the nugget. So both of the ways of approaching this have given us the same result at the end. So we have shown, using the Venn diagram, that they are equivalent. So A and B in brackets and C is the same as A and open brackets B and C close brackets. I'm going to slightly speed up now. So the next one we're going to do is the equivalent for ORs. So we're going to have A or B or with C. So that's A or B, that's C, A or B ORed with C, and because it's an OR, it all goes dark. The other side of the rule, we have A, that's B or C, A or B or C, and again it goes dark. The whole thing, all three circles dark. Left hand side the same as the right hand side. What happens if we have a formula that looks like this, but the operators are different? So this is called the expand the brackets rules. This is very much like if you know expanding brackets in normal algebra. It's a very similar kind of procedure. So we're going to take the first one, A or brackets B and C, close brackets, is the same as brackets A or B, close brackets, and brackets A or C, close brackets. So it's like we've taken the A that's outside the brackets with the OR operator and applied it to the two terms that are inside the brackets, the B and the C, and the link is the same operator as is inside the brackets. Here we go, a proof. We've got A, and then we've got B and C, A or B and C, and it goes dark. And so we've got the whole of the A circle and the intersect between the B and the C circle. And I'm slightly squinting my eyes. This looks a little bit like a head with a beard, goatee beard. The other side, we've got A or B, A or C, and we're doing an and between the two. So we fade the blue and we've got exactly the same shape. Once again, we've proved our statement. Next rule, A and B or C, and we're doing exactly the same thing, except that two operators have been reversed. Where there was an and, there is now an or. Where there was an or, there are now ands. So, once again, left-hand side, A, B or C, there's the two combined, and because it's an and, we fade out the blue, and we've got this. There's three pieces in the middle. On the right-hand side, we've got A and B, we've got A and C, and combining the two together, and because it's or this time, the light blue becomes dark, which gives us the same shape in our Venn diagram as we had for the left-hand side. So something a little different now. Up until now, the rules that we've had have been very similar to equivalent rules that are in normal algebra. These rules, which are called absorption rules, have no equivalent in normal algebra. They're mixed operators, but there's only two variables. Instead, we've got a repeated variable. And what we'll see as we go through is that the variable that's outside the brackets dominates in these rules. So let's take them one at a time. A and brackets, A or B, close brackets, is the same as A. Really? It seems a little counterintuitive. Let's look at it through our Venn diagram. So here's A or B. Here's combining the two. We've got it dark where both of those statements were true. And then because it's an and, we're fading out the light blue. Oh yes, look. So it's the same as A. So A and brackets, A or B, close brackets, is exactly the same as A. And the other one, the other rule is exactly the same, except it's swapping the operators again. So we've got A or brackets, A and B, close brackets. So here's our A, here's our A and B. Here's the two of them combined together, and the significant operator here is the or, so we darken up. Once again, we get A. So A or A and B in brackets is exactly the same as A. The next set of rules we're going to do is what's called the single variable rules. There are, count them, 9 of these. However, they are mostly fairly trivial. Some of them are so trivial that you won't see any changes in the Venn diagrams at all. Let's kick into these. Let's take each one in turn. Here we go. So A and true is equivalent to A. Now we're starting to use these blanket true and false values that we introduced way back at the beginning of the video. So here's A, here's true, here's the combination A and true, and it's an and, so we fade out the light blue. Yes, we can say A and true is equivalent to A. A and false. We're asserting that A and false is equivalent to false. So here's A, here's false, which has got nothing in it. Here's the combination of the two, and because it's an and, we fade out. And although we've got our circle still here, there are no points inside the circle of the A circle which are dark, nothing that is true. So this is the same as just having the blank empty screen. A and false is equivalent to false. Next one, A and not A is equivalent to false. Here's A, not A is the inverse, so it looks like this. Combine the two together because it's an and, I'm going to fade out the light blue. Yes, it's false, there's nothing there, so A and not A is false. A and A equals A. This is so trivial, it's hardly worth dealing with. Here's A and A. Yes, they're the same. Right. Next one, A or false is equivalent to A. Here's A, here's false, here's the combination. Because it's an or, we're going to darken up. Oh yes, look, it's our A circle. Next, A or true is the same as true. Here's A, here's true. Here's the combination, and because it's an or, we're going to darken up, and we get A or true is exactly the same as true. Every single pixel on the screen, apart from where we've got the text, has gone dark. A or A is equivalent to A. Again, another really, really trivial one. A, that's A or A. Yes, we can see they're both the same. A or not A equals true, or is the same as true. Here's A, here's not A, here's the combination, now it's an or, so we darken up. Yes, that's the same as true because everything has gone dark. Finally, not A is the same as A. Again, this seems very trivial. We will just go through the Venn diagram. There's A, and here's not A, and here's not A. Having inverted not A, we get ourselves back to our A situation. Right, that's the easy ones out of the way. Actually, to be honest, this next couple, which are the last couple that we're going to do, are not that hard either. We've got into a rhythm. We know what we're doing with our proofs. Here we go. This is a special pair of rules called De Morgan's law, after a guy called De Morgan who came up with them. There is no equivalent of these in normal algebra, and the feature here is that we have a bracket with two terms and an operator inside, and the whole bracket has been knotted. It's got not operator at the outside. And if you look at the two rules here, what you do is to expand out the bracket, you apply the not to both terms in the bracket, and you swap the operator for the other of the two main operators there, the and the or operators. This is particularly useful in digital electronics, as it turns out. So let's take each one of these in turn. So we start with not A and B is equivalent to not A or not B. Really? This doesn't seem intuitive. Let's have a quick look at it and see if it works out in our Venn diagrams. So here's A or B. So therefore here's not A or B. Everything else apart from that lens shape in the middle has gone dark. And so looking at the right hand side, here's not A and here's not B. And so as we combine the two, and it's an or, so the light blue gets darker, and we find we've got the same lens shape in the middle. Yes, it's true. And the other rule in De Morgan's theorem is looks pretty much similar, except we've swapped our ors for ands and our ands for ors. So we've got not A or B is equivalent to not A and not B. And here comes the proof. So here's A or B. Here's the inverse, not A or B, and that's the left-hand side. Here's the right-hand side coming up, not A, not B, and if we AND the two together, there's the combination, and we fade that blue down to nothing. And yes, look, it looks the same as our left-hand side. So we've done a whole lot of rules, we've done the proofs. You can go back through them and verify them if you want, or you can just have a look at these rules and try and absorb them. I'm just going to do a quick summary now, recapping all of the rules flashed onto the screen for you. Here's the commutative rules, here's the associative rules, here's the expand the bracket rules, here's the absorption rules, the single variable rules, and De Morgan's law, which produces two rules. Thank you and goodbye, friends.